The biggest problem with the internet is that it's not secure. And I want to change this. So let's just conceptualize the internet in a very simple terms. There's a user and a server. This is a very common way of thinking about things. The problem with this is that the server, or whoever runs the server, can manipulate any data in the database. They can censor people on the platform. They can change the rules. They can change how the web application works on any website that you visit. And like, for example, you could even spoof the activity of a user and make them say something that they didn't say. For example, the president, Trump actually did post this. This is real, but you could, if the president of the United States used a centralized platform, you could launch as the administrator of that platform, you could launch a token in their name, which is not good. As you can see, centralized servers are very vulnerable, and this is a huge problem. And the sad thing is that the user has absolutely no recourse whatsoever to any of these attacks. You cannot detect them, you cannot combat them, you cannot disprove them, you cannot bypass them. There's nothing as a user on the internet, as great as the internet is, there's nothing that you can do about it. And this has a lot of downstream implications, which I would love to get into deeper at another time, but just really quickly, this means that users can't trust what they're reading, business owners can't rely on these platforms, so they can't build content businesses, or they can't be developers that are building third-party plugins that are on top of a tech platform. And you can't trust other sites that you integrate. This really limits the amount of that different companies can collaborate with each other. And I think the most important thing is that it forces centralized ownership over tech companies. Since there's this centralized point of control, which whoever controls this server is able to manipulate data and basically control all the rules of the entire platform, that is a centralizing force that requires centralized companies to operate software that we use on the internet. And that is a huge vulnerability. And when we are able to solve these problems, we can then unlock a whole new way of building software. We can unlock new forms of permissionless collaboration. We can have DAOs build software, and we can finance software development with DeFi. There's a lot of really amazing things that are going to open up if we solve these problems. So how would we do this? One way to solve these problems is that we could rewrite the entire internet from scratch. Everything on the internet, we can use these new, whatever the latest cool developer tool in the Web3 world is. A few people have used it, they think it's good, but largely unvalidated. And all these people who choose different technologies for all their different web applications, we can say, you're wrong, you shouldn't choose that technology. Instead, you should use this library that this 19-year-old made and went viral on X. That's obviously not, this is a horrible plan. This is not the way. We cannot rewrite the entire, yeah, we can't do it, exactly. This is not the way to do it. We should enable people to use the tools that they want. Now, there is going to be a lot of new tools that emerge that are going to be great, but if we want to get the entire internet to be verified, then we're going to need to come up with a better idea. Okay. What about zk-TLS? Some people might think of this. Like zk-TLS is something that has been known as a way to take Web2 data and bring it into Web3 and make it verifiable. zk-TLS is really cool, and these teams are awesome that are working on it, but this doesn't solve the problems that I mentioned. It doesn't add security to the underlying apps, the data that's being accessed. What it does is it improves the chain of custody. So if you use zk-TLS and you talk to GitHub to get someone's username and you bring that on chain, what that's doing is it's making sure that the people taking the data from GitHub server and putting it on chain did not modify that data, and they're being honest. And it also does some really cool stuff to preserve the privacy of the user who authenticated to prove that they own that username. So it's a very cool technology. It's something that we will utilize, but it is not going to solve the actual problem of GitHub and Microsoft, the company that owns GitHub. It doesn't solve the problem of them updating the database to change someone's username or to ban a user or to change the rules of how ownership of repositories works. For that, we need to actually verify the software that's running on GitHub's servers. So now if you're still thinking about what is the solution, how do we make the internet verifiable?
Wanted to ask for people who aren't familiar about what zk-TLS is. Like, what's the TLDR on what that does?
Yeah, what I was saying is that zk-TLS is something that will authenticate that you talked to a server with the appropriate certificate, so that it shows that when you present that data on chain, you also have a proof that you actually retrieved that data from the centralized server that you expect to. So after it leaves the server, that data is secure. It's unaltered. It's like a proof that was what was presented. But there's no guarantee about the underlying data from the Web 2 style app that was presented. That can be completely manipulated. And you can just have a proof that's really what they sent you. But that doesn't enforce that any of these problems that we were talking about, any of these problems like manipulating the database, it doesn't prevent any of that. The GitHub can still do whatever they want. And including, they could potentially use that as an attack vector against on-chain applications using zk-TLS by saying one thing for zk-TLS and then changing it later and then messing it up. And you need to have mechanisms for that. Which I'm not saying zk-TLS is bad. What I'm saying is zk-TLS doesn't solve this problem.
And it sounds like there's still a lot of centralized trust that you have to place. Like you have to trust a lot of centralized authorities for this. Yeah.
Exactly. This problem is completely unsolved up until now. A centralized server, like for example, if people are watching this on x.com, X can put any data, they can post anything from our account, they can update our follower list, they can ban us, they can change the rules of the algorithm, they can do everything. There's nothing, they own it, it's centralized, and there's nothing that we can do about it at all. We can't detect it, we can't prevent it, we can't bypass it. Does that make sense?
Yeah, thank you.
Yeah, cool. Okay, so to solve this problem, we can't rewrite everything from scratch. That's just not realistic. We cannot, zk-TLS is great, we should use it, but this does not solve that problem. It solves a different problem, which is a good problem. What if we used ZK proofs or other types of proofs on the server? What if we actually prove the computation running on the server? This is a good idea. Let's look into how this might work. The user makes a request to the server, and then the server runs a ZK VM. And the ZK VM will, inside the ZK VM, it'll run two pieces. One would be the request handler, which would be just a function of code that executes when that request comes in. And then the other thing would be the database. So you can think about the database as, let's say I post something new on x.com. I post some update. The database did not have that post in the database before I made that request, but I send that request to post that new data, and then it adds it to the database, and now the database has been updated. So before the request, there was what you can call the initial state, and after the request, there is what you can call like the final state or the next state. And this is what's called a state transition function. So you have a function that, given the previous state of the database and the new data coming in from the new request, you have the new state, which is the new state of the database. And I know that might be like a little bit technical and a little bit dense, but this is essentially how rollups work. And we can use this exact same architecture on the server. Just to be clear, you send the request in, it runs this request handler, it accesses the original data from the database and then it updates the database. And then it can send a response to your browser or to your application with the proof that the response is correctly generated by the request that you sent. And it can update the next state for the next request that comes in so that you can use that state when you're handling that next request. And this is a really great pattern and this will work. But there is a problem with this. The problem is that we don't know what the previous state must be, because it's a little bit, we don't need to go into all the details, but basically we don't have consensus over what's in the database. If we just use ZK proofs on the server, we don't know what the old state of the database is. So when we have that incoming request, we can prove that there was some state in the database that we used against the incoming request, but we can't prove that was the canonical official prior state when generating the new state. How do we solve this? Data availability layers, that's what solves this. So we are going to focus on Celestia for the rest of this presentation. So how does data availability fix this? Well, the truth is that this is a bit of an oversimplification. So I want to go a little bit more in detail. just to give you, I want to show you the exact place of the infrastructure where the DA layer actually adds verification. So the way I like to think about the internet a little bit more in depth is that there's a user, and the user is connected to an internet service provider. So in the United States, there's Verizon, AT&T, Comcast, etc. These are internet service providers, and they bring internet to your home. And so what happens is you connect to your internet service provider, and then there's many different internet service providers, and all of these connect at what's called an internet exchange point. And so this kind of aggregates a bunch of networks. And this is where something like AWS would connect to. So when you are, so in a sense, how an end user is connected to a data center with a server in it. So now also keep in mind, there's many people with home internet connections. So there's going to be a lot of individual users with slow connections, maybe 100 megabits per second, or honestly much less than that sometimes. And these are all going to be connected to an internet service provider, which is going to aggregate all of these connections. And it's going to go to like local nodes, and they're going to have this backbone. And essentially, it's going to come from all these different homes, and it's going to all go at some point into a single wire, more or less, or fiber optic cable going into an internet exchange point. And then this internet exchange point is going to have, really, I'm simplifying it, basically a single wire that's going into the data center, or at least you can say for sure the server is just going to have a single like fiber optic cable going into it. And
a wild way to think about it, honestly.
Yeah, it is. It's actually really interesting to learn about this stuff. So let's say you want to upload a picture of the Mona Lisa. How is this going to happen? So what it doesn't do is it doesn't just send it all at once, because if you can only send, technically, although it's very fast, you can only send one bit at a time. There's a little bit of nuance to that, but let's just pretend like that's true. You can only really send one bit at a time. You can only read one bit at a time into your computer from a fiber optic cable. So what it does is, you have all these people that are using the internet at the same time, and yet when they all connect to the data center, it's all going through like a few cables. So how does that happen? What it does is it breaks the data into packets. So it'll break up this picture into smaller chunks, and then it's going to route these packets across this infrastructure. And the order can get mixed up. There's no guarantee that it gets delivered. Sometimes packets get dropped, and there's all these types of unreliability that you have. But what happens though is that at some point, these packets go directly into the server, and there's just like this fiber optic cable going into the server, and that server is reading one bit at a time, and it's just really quickly doing it because it's a very fast connection. But then it gets this packet, and then it gets this packet, and then it eventually gets the whole picture. And so there is, at this end point, there's this sequential, canonical, like single lane highway of data where there's a specific order of when that data came in. And that is like at the tail end of this flow. And that's not to say this whole thing is like a first in, first out queue. This is not a reliable system, but there is like a canonical order of bits that came into the server that's running the software. That's just how it works. And like that is essentially the ultimate bottleneck for the application, is the connection going into it. And there are other bottlenecks. And for the user, the bottleneck would be how much data they can bring into their home. Usually that's much less than what the server has, although it could be more. And so like this right here is essentially what DA layer is making verifiable. It's saying it's running on top of the internet. It's not part of the internet infrastructure, but you should think about this as a bandwidth verification tool. Something that says this is the order that the bits came through, and as we send them to the server for computation. And so if we go back to our problem where we were saying we don't know what the previous state should be, how do we know what the data should be in the database? How can we trust the proof if we don't know that previous database's data was correct? The answer is if we can use Celestia to very efficiently understand what was all the data that was sent through, what was the correct list, then we can use the proof to prove that the database state that we were using for our state transition function was actually the correct database state. And doing, like by verifying Celestia, we can use that in conjunction with a proof to prove that the entire thing is accurate. And this is how rollups work. But this also works just in general. And notice I didn't talk about any libraries or frameworks or anything like that. This is just in general how you can verify software on the internet. And I'll stop there for a second. Do you have any questions?
I don't have any questions right now. There aren't any in the chat, so I'm gonna let you roll with it.
Awesome. Okay, so now let's put all of this together. When you put all this together, this is everything that we need for a fully verifiable internet. Like we have the DA layer checking all the incoming traffic, verifying all the incoming traffic and putting it in order. And then we have proofs that once the traffic comes in, we are proving that this was handled properly. And when you combine this with several other problems or solutions that are already solved, like digital signatures and bridging and ZK-TLS, which is also a very useful thing. If you wanted to have a verifiable application talk to a non-verifiable application, that's the best bet that you have. So if you combine all of these things, you can imagine basically having an entirely verifiable internet. You can imagine having a data center that's world-class that can host. You don't think that you're going to exhaust the resources of AWS. You just go and you host your app. You're not going to exhaust the resources of AWS. So you can imagine for the people that demand verifiable applications, that they would be able to do it affordably and have viable businesses and basically make software that is verifiable and affordable and works and is interoperable with crypto. So this is what I think we should have for the entire internet. Just like as we adopted HTTPS, where you're validating the certificate of the server that you're talking to, we can take that a step further. And if we have a very good developer experience, we make this easy, we build this into the infrastructure, at least as an option, we can have a whole bunch of adoption on this. Now, but is that realistic? Is it realistic to verify a giant portion of the internet? Is that something that we can actually do? Yes, I think it's realistic. Let's do it. Yeah, we do not back down from a challenge. Exactly. Okay, let's think about this. Okay, so ZK proofs are currently 100,000 times more expensive than normal computation. Last time I checked. That's really expensive. That we obviously can't just do everything that we normally do as a ZK proof. That's not gonna. We're not there yet. Now, there are other techniques of proving that are not ZK proofs, like we can use fraud proofs, we can use actively validated services, we can even use Comet BFT, all these types of things. There's a lot of techniques that will add either a lot of security or just some security, depending on your needs, that can replace ZK proofs, which are still more expensive than normal computation, but they're in the same order of magnitude, roughly, or maybe just a little bit more expensive. But ZK proofs are by far way too expensive to be used at scale right now. But they are the holy grail because they are very efficient and they are very secure. But let's think about these numbers for a sec. First of all, people already operate high margin software businesses easily. Compute is honestly less than 10% of total expenses. But let's just conservatively say compute is 10% of your total expenses as a software business. That means you actually have a decent margin that even if compute was 10 times more expensive, your business could still be viable potentially. And then like people have 90% margins on serverless platforms. And these serverless platforms are like 10x more expensive than bare metal. So if you look at this, you can see how there is like this giant software margin that is there that could be there. Like, I think a lot of stuff would still be viable, even if the underlying cost was 100 times more expensive. The other thing, which I think this is like a much less good assumption, but I just put it in there because these other ones I think are actually conservative. Not everything needs to be proven. Mostly it's just state updates, and it's hard to know what the ratio of state updates to reading data is. But like, you could optimistically think you can get another 10x just from not proving everything, just proving the things that you need to. If we're already doing the computation that we're doing, but there's already, and we need to, right now, we don't want to pay 100,000 times more than we currently are to do what we do. But we do have this 1,000x margin to work with. So maybe if it was if we could just do things 100 times more efficiently, that might actually be viable to prove most computations. And so I think within 1 decade, like Moore's law will deliver us those types of scaling results. But I also think we have such good teams working on this, saying to risk zero, and so many other like prover networks and ZK-VM teams and engineers work. There's teams doing hardware acceleration for ZK proofs. I couldn't be more bullish. I think we're going to get massive amounts of scaling just from the engineering side. And yeah, I'm very bullish on being able to do this in the foreseeable future, to be able to do ZK proofs on anything that you want to at a good cost.
I like the way you broke that down a lot. Yeah, thank you.
Okay, now what about Celestia? Celestia has a little bit bigger of a challenge than ZK proofs, because Celestia needs to scale 1 million times to match a modern data center. And so Celestia has about 1 megabit per second of bandwidth. It might be a little higher now. And then data centers have at least 1 terabit per second. Like a big one will have 50 terabits per second or something, maybe at most 100. But a small one would have 1 terabit per second. And I think it's safe to say if we could have, I'm talking about a real legit data center. If we could have a whole data center that's verifiable, you don't think you're going to go on you don't think you're going to exhaust the resources of fly.io or something, right?
No.
You're not going to. Like there's plenty of bandwidth there to be had. So I think 1 terabit per second is a really good target for what we should try to scale to. And okay, so can Celestia scale 1 million times? I feel ridiculous saying that they could, but actually let's look at this. So first of all, Celestia has already delivered a 1000x improvement to Manta. Manta is the first roll-up to launch on Celestia, and they've already delivered a 1000x improvement over Ethereum. Now that cost calculation is a little bit more complicated. It has to do with compute costs, not just bandwidth, et cetera. But it's already happened. A 1000x is not an impossible thing to deliver. The next thing I'll say is that Celestia's current roadmap is it has a 1000x increase. So we can get from a megabit per second speed to a gigabit per second speed. And that's just the current plan. And maybe you can correct me if I'm wrong, Josh, but talking to people on the Celestia team, I think this can go above 1 gigabyte blocks every 2 seconds, which is what I believe is the current target for the roadmap. That's a kind of an arbitrary stopping place. That even with the current techniques, the current plans, I think it could go higher than that. But it's certainly true that as you approach 1 terabit per second, it gets a little ridiculous. A gigabit per second is, I've been thinking about the engineering of this, and a terabit per second is really hard. So
yeah, it's up there.
I'm not saying that's an easily solvable problem, but I think that over time, we can get there. And with good engineering, as we've been doing, I think that this is possible. And the only other thing I will say on this is that we only need to verify the writes, not the reads. So a lot of the bandwidth is for reading, not writing. And so again, I think 1 terabit per second goes a lot further than you think, and 1 gigabit per second goes a lot further than you think for this type of architecture. Okay, last in this section, I just want to mention this quote that someone posted on X, and I forgot who posted it. I would give them credit, but this reminded me of this quote by Alan Kay. It says, "People who are really serious about software should make their own hardware." And I really am starting to think of Celestia as almost a DePIN network, and Celestia is not building hardware. It's just not. Yeah, no, they're not building hardware. They're not actually doing DePIN. But the logical conclusion is that people would, if we were to follow this architecture to make a verifiable internet and verifiable data centers, the logical conclusion is that it would be very difficult to run a full node, a block producer. And that would be a highly professionalized thing, which would actually have physical infrastructure that would need to be spun up in order to support this. Yeah. And of course, it could be verified at home with light nodes, which is the great part. Yeah. So I think that's a really interesting perspective. And so
I would say even in that case, we're going to put all of the nodes are going to be on the user end, like on the client side. So you can just verify things yourself.
Yeah, right. It's very important.
Like a terabyte's definitely not out of the question, because with light node optimizations, like engineering optimizations for how blocks are made and things like that, I think it's definitely possible one day. Yeah.
Yeah, and I think it's really important to hit that point. That's a great point. People will be running light nodes, so they don't have to trust the people that are producing the blocks. There are going to be big companies that can process a lot of bandwidth with specialized compute hardware that are going to be running this like next gen data center. They might also be running provers alongside Celestia nodes. Who knows the kind of stuff they'll be up to. And but the thing is, these will be professionals. Will be very expensive, and it will be a great service for people. But at-home users will be able to verify this with a light node. So they could do it on their phone. They can check what these big companies are doing on their little small device, which is really awesome.
I was actually, I want to toss in this like random fun fact. I was going through old notes that I came across this weekend, and I had something from one of Mustafa's talks about how it's more likely that you have a photon hit your RAM and flip a bit than it is for you to get the wrong result from sampling 100 times. And I don't have the math on hand to back that up, but I think that's something that blew my mind then, and just shows the power of the math here with data availability sampling.
Yeah, if I recall correctly, every time you sample, that the odds of not finding the missing data are in half. They're cut in half. And when you double things, basically your security doubles with every sample. That's one way of looking at it, although maybe that's a bad way of looking at it. Yeah, I think like 17 samples is like 99.999%. If you keep doubling up to 100 times, you're going to get to an astronomically high amount of security. It's ridiculous, actually.
And then we can wrap that up, but it only would take 1, 2, 3, like around 10 doublings to get from 2 megabyte blocks up to 1 gigabyte. So
that's right. Yeah, so it's very doable. It's going to be really hard. I'm going to say this. It's going to be hard. It's going to be really hard, but it's doable, and it's so worth doing. Like we're talking about providing the security that Ethereum and Bitcoin and these very secure established networks provide. We're taking all the benefits of those systems, the reason we call those cryptocurrencies, taking that and giving that to all software on the internet. And this also helps with interoperability. And we can talk more about that later. But this is very worth doing. It's very worth doing. This is the end game. This is how I see things playing out. So I think over the next decade, because with Moore's law and Nielsen's law and all the engineering breakthroughs, I think we can maybe not have this all set up, but we can be well on our way to having built this over the next decade. But you don't need to wait for the whole internet to be able to go on this type of an architecture and build software in this way to do it now. You can actually still build this stuff right now. So this is an amazing vision. It will be great when everyone does it, but you can do it right now. So how?
Let's do it.
Well, Chopin framework. This is what Chopin framework essentially does. In the previous explanation, I was talking more on this conceptual level, talking about IP, TCP IP as a level of abstraction for thinking about it. I don't know exactly how Celestia is going to turn out when it scales. I think a lot of smarter engineers than me are going to figure out the best ways of doing that. So I was just putting forth a potential vision for that. But with Chopin framework, this is on a different level of abstraction. It's above that layer of TCP/IP. It's on the HTTP layer. But essentially, it takes that architecture that I just talked about and implements it on the HTTP layer, which is the layer that the web browser uses. And it's also the layer that a mobile app would use when they do REST APIs in their backend and stuff like that.